transaction or in a block or in like the peer-to-peer protocol, you transmit the size of something. Well, you could use like 4 bytes always to represent the size of something, but then that would be efficient if you're only, it would be inefficient if you're only ever transmitting a small number. So, and also, not just for network efficiency, but if everybody stores the blockchain, you know, you want to use a small compact number format. So Bitcoin has its own custom number format that's called compact size. I call it varent because it's simpler. And I'll explain how this works. So it's at least 1 byte and it's up to 9 bytes long. And so the way this works is there's a header byte that can either represent the size, so like if you have like 250 for instance, can fit in just 1 byte. But if you go over 253, like 254, then what that means is, okay, I'm going to follow it with 2 bytes that represent little endian unsigned value. And if the header byte is 255, then it's followed by 4 bytes, and if the header byte is 256, then it's followed by 8 bytes. So that's how the varent works. So this lets you just, you know, efficiently store lengths.
So, I'm sorry, the word varent is a Bitcoin-specific word, is that right?
Yeah. It's in the source code. I don't know the history of this. In the source code, it's called compact size, but a lot of people call it varent. Like when I implement it, I call it varent. It's just easier. But there are other notions of varent, which this is not. So just, you know, there are many different ways people throughout history have come up to represent a variable size integer, but this is just, you know, yes, it is a Bitcoin-specific format. This is Bitcoin varent. So varent has, so here are just some examples. Like on the left there, you see the binary format, and then on the right is the corresponding decimal format. So one interesting property of varents is that there are degeneracies. Like you can write the same number more than one way. So the number 0 can be written many different ways. You can say it's literally just the number 0, 1 byte, or you can start with a header byte and say it's going to be followed by 4 bytes, all of which are 0. So this is just an example of something in Bitcoin where there might be more than one way to represent some data. And so if you're trying to do something exactly the same way as somebody else, you have to be aware of this. So yeah, we'll talk about that more later, but there's more than one way to represent 0. And these are just other examples. You can represent quite large numbers all the way up to, you know, 8 bytes of value, whatever the largest number of that is. It's very big. 2 to the And Bitcoin, of course, also uses big numbers because 8 bytes is not long enough for Bitcoin. Because the 2 reasons. One is the curve that Bitcoin uses, SECP256K1, is 256 bits. It uses 256-bit numbers, which are 32 bytes. So we also have to have a notion of big integers. Yeah, I think right now in the source code, Bitcoin has at least 2 different ways to do this. One is like the OpenSSL big number, and the other is there's a new library that the core developers are writing called libsecp256k1, which has its own new number format, but it's basically pretty much you see up to about 32 bytes. I'm not sure if 33 bytes ever occurs, but it might, just because in signed magnitude format, if you try and represent an unsigned number that has the most significant bit flipped, you have to use another. So it might be 33 bytes. But in any case, this would be like, you can have like variable size. It can be any size of number. And this occurs in like a transaction in the form of a public key, so we'll talk about that. And then also hash functions. Hash functions are also interpreted as numbers sometimes. So like SHA-256, 256 bits. So that's often interpreted as a number, and it's a 256-bit number. And then the example I have there on the bottom is the order of the curve of Bitcoin. So that is a number that is in like the Bitcoin source code. There's yet another number format. So this is something called script num in the source code. And what this is like you can perform operations on numbers in a script in Bitcoin. And Satoshi implemented just a new novel form of number. I don't really know why. Well, actually, I can guess why, which is that if you add 2 very large 4-byte numbers together, you might have like overflow, which is where it can't be represented in 4 bytes. So the way Satoshi handled this is, rather than throw an error or something like that, it just overflows to a 5th byte. So there's this custom number format that if you use the operations in a script like adding or subtracting or whatever, there are like dozens of these operations that use just numbers. It's this special number format. It's between 0 and 4 bytes normally, but if it overflows, it can use additional bytes up to like internally it's represented as a long, so it's up to like 8 bytes. And fixed points also occur. So fixed points is where you have a fixed number of decimal places. So when you write down a number of bitcoins, that's always a fixed point, decimal number. It's not floating point, it's fixed point. They're always exactly 8 decimal places. If you have more than 8 decimal places, it's not valid. So this doesn't really occur in the protocol because internally, Bitcoin always represents numbers or values as satoshis, which is the smallest unit or 100 millionth of a Bitcoin. So these are only ever like displayed, so they're not really in the protocol. But they're, if you display a value and you convert it to Bitcoins, you basically move the decimal point over 8 places. So that's what a fixed point is. And floating points also occur. So there are a number of mostly non-significant places in the source code that use floating points. Like I did this yesterday. I just searched, well, what is all the points? There are, like, if you just do various calculations for display purposes, like if you're dealing with time or something, sometimes it uses a double. The one significant place that I'm aware of in the actual protocol is the difficulty is represented with a custom floating point number. And so this actually occurs in a block, and we'll talk about this a little bit more later. But there is a floating point value that's relevant to the protocol, and it's difficulty. I think, was that all? Okay. Okay, so yeah, so that's all the number formats. This is like, I'm not aware of very many number formats that are not used in Bitcoin. So this is just the catchphrase. If a number format exists, it's used in Bitcoin somewhere. It's not a matter of if it's used, it's where does Bitcoin use this number format.
Ryan, why?
Yes. Why? Because Bitcoin was written by one person. I don't know the real reason why, but I think what happened was, like, if you understand like C++ on x86 machines and you're using OpenSSL and you're trying to make something like Bitcoin work as fastly as possible, it's just easier. So I think the reason why, like, why does Satoshi use big Indian numbers and little Indian numbers? There's no reason to use both. Just pick one. I think the reason is because C++ on an x86 machine uses little Indian. That's just how, like, an int in C++ is little Indian, and so if you just cast that to bytes, you get little Indian. On the other hand, OpenSSL deals with a lot of big Indian numbers. And big Indian is also sort of intuitive. So if you ever try to deal with it by hand, you'll intuitively do it big Indian rather than little Indian. So between OpenSSL and C++ on x86 machines, if you're just doing things the easy way, you'll mix little Indian and big Indian. That's my guess. I think Satoshi just did the easy thing that worked. But other than that, I don't really know. I don't think there's a good reason that I'm aware of. But
most network protocols use big Indian.
yeah, and Bitcoin does not really. Like, if you represent like a size, it'll send the bits are big Indian, but the bytes are not. So like varent, it sends a little Indian value. So yeah, but the bits are always big Indian. Insofar as that's relevant. Yeah.
Are there efforts to standardize this to make it simpler and more consistent?
So that's a really good question. So do we want to standardize this, right? The short answer is we want to standardize this in a way so that people can easily re-implement this, but there's really no easy way to change the protocol. So there's no way we're going to go back in and make things that are little Indian, big Indian, because people are already running Bitcoin, and if you change the rules, you're no longer compatible with everybody else. So if you tried to make a change like that, you would have to get everybody to switch at the same time, or you would just go off on a fork. So we're probably just stuck with it. So that's what, that's part of the reason why I'm going in and explaining all the details, which is like if you actually deal with this stuff, you will have to know this, and I'm pretty sure we're just stuck with this forever. So you'll have to know big Indian and little Indian and all these other formats. Although people like myself are writing libraries that understand all this stuff, or people write, there are people like a Block Cipher and Chain.com if they're here. they make APIs where you may not have to think about it if you just use somebody else's API. But if you do implement it, yeah. The reality is you'll probably have to know. All right, so so public keys will occur in transactions. So a public key is two values, an X and a Y value. And so Bitcoin, I've mentioned OpenSSL. So Bitcoin uses OpenSSL. And so a lot of the number formats come from OpenSSL. So OpenSSL represents public keys in DeOur format, which is just what it's called. And there are actually like 5 different ways to write down a public key, most of which are almost the same. I think I have, so just, you probably have learned this in the previous lectures, but a public key is a point that can be found from a private key, which is a big number. So big number times G gets you the public key. So that's where the public key comes from, X and Y. So a public key, normally you see it in the compressed format, which is where the Y value is not represented in the public key, rather whether it is odd or not is represented. Because you can derive the Y value from the X value if you know if the public key is odd. So you write down just one byte that represents whether Y is odd or not, and then the X value, which is 32 bytes. That's how we do it these days. But originally, Bitcoin used uncompressed public keys, which is like the standard default obvious way to do it in OpenSSL, which is where you write down just the number 4, which is just DER format, starts with a 4, and then X and then Y. And we stopped using this, we as in like we the Bitcoin community, because it just uses extra space in the blockchain that you would rather not have to use. Why use that Y value and take up 32 bytes of precious storage with like every transaction when that could be 0 bytes? And there are just these other miscellaneous formats that Peter Wool looked up. Like Peter Wool is one of the core developers, and years ago he was investigating OpenSSL and discovered there were several other formats that we had not known about before. And so you can start the public key with either a 6 or a 7 also, but these like, I don't think they might occur in the blockchain, I don't know, but they're basically obsolete now, and any new software should not be producing public keys that look like that. You should always use compressed format just because it's the smallest. All right, and so the other final, it's not a number, but sort of value that occurs in a transaction are signatures. And this consists of 2 numbers, R and S, which are just two big numbers, not unlike a private key, except it's not a point, they're just 2 big numbers. And 256-bit numbers. The obvious way to write down what a signature would be you just write them down in order. They could be 32 bytes, you write X and then you write down Y. Unfortunately, this is not what Bitcoin does because that's not what OpenSSL does. So the definition of a compact signature is like the obvious thing, where if you, Bitcoin uses this if you sign an arbitrary message, but it's not used in transactions. So if you sign like data, it'll use the compact form. But that doesn't occur in the blockchain. It's only something you use sort of on top of Bitcoin. Unfortunately, the format that is used in the blockchain is DER format, which looks like this. So here's a DER signature. So it consists of, it's actually complicated. It consists of a DER signature followed by a hash byte. And if you, I don't explain what a hash byte is in this talk, but if you want to know, I can explain it later. It has to do with the different ways of hashing a transaction. So it's a DER signature and then followed by a single byte representing the hash type. And the DER signature looks like this. It looks like it starts with a hexadecimal 30, followed by the length of everything that follows, followed by the number 2, followed by the length of the R value, followed by R, which can be anywhere. It can be, hypothetically, it could be 0 bytes, but usually it's going to be about 32 bytes. Followed by the number 2, followed by the length of the S value, followed by S, and then that's it. And then if in the blockchain, and then it's also followed by the hash type. So this is how they actually look in the blockchain. There are all sorts of weird gotchas here, where like if you're parsing a transaction, if you actually write this stuff down, you have to understand the format correctly, and you can't like throw an error if Bitcoin does not consider it an error. So parsing it correctly involves throwing errors in exactly the same way that Bitcoin throws an error. So for instance, if the length of this is wrong, but Bitcoin doesn't care if the length is wrong, then the length is not wrong. So in other words, like if you write down like, okay, if you don't write down, if the number starts with a 0 and you include the 0 byte at the start, that's an example of a degeneracy. So like, if the number can be represented as 31 bytes, but you choose to represent it as 32 bytes, there are two different ways to represent the numbers. That makes sense, like if it starts with a 0. So that is like not standard, and we're trying to make it so that nobody creates these 1 byte extra long signatures. But as of today, it's not an error to do that. There are signatures that look that way, so you have to sort of understand that. All right. Are there any questions about all that stuff? So those are sort of all the major things you see in the blockchain in a transaction. I'm going through all this stuff because we'll build up what a transaction is, and you'll see all these pieces fit together. All right. So the next thing.
I have a question.
Yeah.
So one of those on the previous slide, there was these R's and S's.
Yeah.
Are you going to describe what those are at some point?
I'm not going to explain ECDSA, but
those are components.
They're components of a signature. So a signature consists of R and S. Okay. R is a big number, S is a big number, and if you follow ECDSA, so ECDSA is a signature algorithm used by Bitcoin. You start with, if you want to sign data, you have a private key, and you follow the ECDSA algorithm. So you have to take the data you want to sign is usually like a transaction. Normally, you do not want to sign the actual transaction because that's a very, very big number. If you interpret it as a number, you want to hash it and get something that's 32 bytes so that your calculations run fast. And then you follow the ECDSA algorithm using the hash and the private key, and it produces two numbers, R and S. And then if you run it through the validate or verify function, you plug in what R and S are, and then you plug in what the public key is, and then what the hash is, and it'll tell you whether it's valid or not. So this is, like, without studying ECDSA, I can't explain what it is, but R and S are the numbers that constitute a signature.
Right, thank you.
All right, so then, so this is, I think this is like sort of, well, one of the last things here that's in a transaction. So these are opcodes. Opcodes are like the commands of a script. So Bitcoin has a script language. It's very size efficient. All the commands are just 1 byte. So these are just an example. There are pages and pages of opcodes. So like I'm not showing every single opcode here, but these are just some of them. And they're just 1 byte. So a script just consists of a series of opcodes, except that some of the opcodes can be push data opcodes. So your script will contain a number of opcodes, then something that says push 3 bytes followed by 3 bytes of data to be pushed. And so in a nutshell, the way the Bitcoin scripting language works is there's a stack and there's an alt stack, but there's no heap. So you can push things to the stack, you can pop things from the stack, you can perform an operation on the things on the stack, but there's no pointers, there's nothing where you can just dynamically allocate arbitrary amounts of memory or something like that. There's just a stack. There's also an alt stack. So you can copy things to the alt stack and then copy it back again, stuff like that. So here are just some examples. So here's just a completely arbitrary example that I wrote down. Op5, op5, op equal verify. So this is just pushing the number 5 and then pushing the number 5 again, and then verifying that the two things on the top of the stack are equal, which would verify to true. And then another example is pushing just data. So in this case, you're pushing 3 bytes and then pushing 3 bytes, both of which are equal, and then running op equal verify again, which should return true because they're both equivalent. Okay, so now we're getting somewhere. Okay, we've now discussed like all the sort of really minor basic elements that are in a transaction. If you understand all that stuff, you get all the details. So now we'll talk about inputs and outputs, and then we'll have built like an entire transaction. So inputs consist of, so it's a link from a previous transaction. So it consists of the hash of the transaction that you're linking from, as well as which output you're linking from. So if somebody had previously sent you 5 Bitcoins, there is a transaction somewhere that says, it has a script that has your address in it, and it's sending 5 Bitcoins to it. That is an output that is numbered. So you reference that transaction, that output. Then the length of your, what's called the script sig, as a variable size integer, followed by the actual script, and then followed by something called the sequence number, which is mostly not used, but if you use like payment channels, they're used. But in sort of the standard, the idea of a sequence number was just to be able to update a transaction at a later date. So they're mostly not used, but in any case, this is what an input looks like. You're just linking the previous transaction or the previous output, and then what the script is. And so I've got sort of what types of numbers they are listed there. So here's an example of where like 2's complement shows up because in the source code, if you cast you'll see things like casting -1 to an unsigned integer. So what the hell does that mean there? An unsigned integer can't be negative. Well, the way that works in C++, it is defined. It takes the 2's complement version of it and then, interprets that as an integer, which if you do that, it's a -1 turns out to be the highest possible 4-byte value. So that's where that comes from. So you see stuff like that. So sequence numbers are, yeah.
Does that mean the transaction can be changed later on? Because I thought once it's put in the blockchain, it's...
Once it's in the blockchain, it cannot be changed.
Okay, so the sequence number is possibly before it gets to the blockchain.
Yes. So the way you would normally use a sequence number is, it's sort of you can sign a transaction with a particular sequence number in it. And as far as I'm aware, there's no rule on I think you can have any sequence number and it can get in the blockchain. But it's just a way of signaling if you're off blockchain and you're sharing a transaction with somebody, you can update it and there's a value in the transaction that can be changed. I'm not aware of any protocol rules. I'm pretty sure you can just use any sequence number and it doesn't actually matter, as far as I'm aware. Yeah. Okay, so those are inputs. So outputs contain the value that you're sending, which is it's a 64-bit number, and it's just unsigned integer, 64-bit number. There's a check in Bitcoin where it cannot be higher than max money, which is 21 million. And then it's just the length of the script and then the script. So the outputs are quite simple, just the value that you're sending. Yeah.
I don't know if it would be helpful for other people, but for me, while you're going over this, it might be helpful to refer to this diagram.
Yeah, definitely.
If these outputs are actually spend Coinbase TX out or standard TX out, there's a bunch of things to say output.
Oh, okay, so yeah, I'd have to look at it, but so you're just saying for starters, yeah.
Just take it, I don't need it.
I remember it well enough.
Okay.
Yeah, because I remember the Coinbase stuff. So
Okay.
it's probably just it's showing multiple examples of what the inputs and outputs can be. And it's showing, I think it's just showing a Coinbase. It's probably showing a Coinbase input and a Coinbase it's probably spinning a Coinbase or something like that.
Yeah.
They're just examples. It's probably not a valid transaction.
I see.
But it's examples of what types of inputs you can have. So he's just talking about that plot I showed at the very beginning of what a transaction looks like. And yeah, so I would look at that as we go through this. And all it's saying is it's just giving you specific examples. So
But all the outputs listed here are probably in this format here.
they are in this format. Yeah, all the inputs and outputs are in this format. Yep.
Got it. All right.
Okay. Okay, so we've covered everything. So now we can talk about what an actual transaction looks like. So now we've sort of come, yeah.
Sorry. So the script, it can be any size?
Okay, so